Hello and welcome back to Calculus 1, section 3.9, derivatives of exponential and logarithmic functions. A lot of stuff to remember and review, and then some new things as well. I'm going to start with exponential functions, and then we're going to go into logs. Formula which you already know. The derivative of e to the x is? There we go. Perfect. Since you synchronized that so well, you might want to try synchronized swimming next. The next formula is the one that you also know, and that is the derivative of e to the f of x. This is your basic chain rule. Derivative of e to the f of x is e to the f of x times f of x prime. This formula is going to get this purple box because most of your problems that are exponential problems, 95%, 98% of them will be this formula, which you already know from your chain rule. This is the basic chain rule applied to the exponential function. You have seen problems with this earlier. But if you notice, both of these formulas that you know from before, even though the second one has a function in the exponent, have a limitation. And that is base is always e, right? So what is the general case? Right? What is the big boss? It's b to the f of x. So the formula b to the f of x allows you to have any base. So you can have 2 to the sine x. You can have 7 to the whatever, x squared minus 3. So this is the boss equation. However, the one that I boxed up there is going to be the one that you use most of the time across all of the courses, including Calc 2, Calc 3 differential equations, and your sciences later on, engineering. They will all use this thing, even though it's not the most general case, right? This is the general case here. So it goes b to the f of x times f prime of x times ln b. So as a boss equation, it does get the purple box. I'll write general case, but then I get to write here most of the time we use this. Because most of your problems are going to be that. As I said, 95, 99%. So since I mentioned, what is the derivative of 2 to the sine x? Well, derivative is, you copy, right? You always do that with exponential. You always copy it, times derivative of the exponent, which is cosine x, and then times ln of the base 2. That's it. ln 2 is a decimal number, right? And the rest has variables in it, so that's where you stop. I also mentioned something with base 7 raised to the x cubed, let's make it up, minus 5x plus 2. Same deal. You copy the exponential part the same, times the derivative of the function is 3x squared minus 5 times ln 7. In time you learn and grow to love exponential function because it has the easiest derivative that you can possibly think of, right? You just copy and add the chain and you're done. So we love exponential functions, and we are lucky that most of the stuff in nature works out to be exponential function. We talked about garbage decay, and we talk about carbon dating, and we talk about nuclear decay, and we talk about population rising or falling, charging, discharging batteries. We're talking about, in physics, the simple harmonic motion with dampening. All of these things have exponential function in it. And metabolizing drug in the blood, right, in the body, it all has exponential function, and every single base is e all the time, which is why we have that formula on top, right? But then certain cases would have base 10. Chemistry would have pH calculations, and they will be base 10. In physics, stuff involving waves will also have base 10 calculation. Richter scale for earthquakes, base 10. Every point of a Richter scale describes the earthquake that is 10 times more powerful than the one before. So when you look at the earthquake on scale 4 and 5, right? Not as insane as 6, 7, 8, 9, right? 9 is pretty much just a level, yeah, flat plane. That's 9, because 9 is 10 times stronger than 8, and 8 is 10 times stronger than 7, and 7 is 10, right? So if you have a tremor at 5, right, 9 is 10,000 times stronger. So yeah, not a joke. So your calculations later on, when you move to the 300 level, 400 level courses, and you have to take derivatives, and you will be taking derivatives, trust me, these derivatives will have exponential functions, and very few of them will have base 10, which is the reason why your calculators have just 2 buttons. They have ln button, and they have log button. We'll talk about that. Well, now we go to the second. This is like a three part, right? So now we talk about logs. It's a pretty good log, right? I've been drawing log for years. Should be better. Before I go into any of the calculus, I am fully aware that pretty much logarithmic skills are non-existent, right? So let's start at 0. Before we jump into any of this story, what's 2 plus 3?
5.
Excellent. And now we go 5 minus 3 is? And 5 minus 2 is? We have the chance to undo, right, and get both of these 2 and 3 going. How about 2 times 3?
6.
Skills. 6 divided by 3 is?
2.
And 6 divided by 2 is?
3.
Nice. So now, what is multiplication? Multiplication is fast repeated addition, right? Instead of you going 3 plus 3 is 6 plus 3 is 9 plus 3 is 12 plus 3 is 15, you just memorize the shortcut 3 times 5 is 15 and you're done with it, right? But essentially, multiplication is fast addition, fast repeated addition. And just because we want to be lazy, we are able to be lazy by memorizing multiplication table. Do you have to know it? No. Go ahead, add, right? 127 times 63. 127 plus 127 is 254 plus 127, right? And, right, you go all the way down to, right? So it's a convenience thing. Now we have exponents. So 2 cubed is 8. And the cube root of 8 is 2. How do I get 3? Because we were able to get these 2's and 3's. So how do I get 3 back?
I'm saying it wrong. I have a visual in my head.
You have a visual in your head. Great. So if
Log base 2 of 8.
yes, log base 2 of 8 is 3. That's where it fits in the universe. What is log? Just mathematical operation, just like addition. Now, why do you discriminate against it? Well, A, you're awful people, right? First, we're all awful. B, probably because it has letters instead of a cute symbol, right? If this was 2 heart 8 equals 3, you would have no problems, right? Right? If you had a symbol like all other operations have symbol. But now because this one has letters, it's like, ooh. So log is a way to undo exponents. It's inverse for exponents. So we write the most important formula for logs as inverse of exponents, and there is a conversion rule between the two worlds, which goes like this. A raised to the b equals c converts into log base a of c is b. So we understand now that log belongs in arithmetic. It's calculation. It's a very nasty calculation, but it's a calculation. So, is log a function? No, because you can't call addition a function or multiplication a function. How do you make a function out of 2 plus 3? Well, you replace either 2 or 3 with x and you create a linear function, right? So if you have x plus 3, then you know it's a linear function, right? You can say f of x equals or y equals. If you go and say 2x, right, it becomes a function. If you go and say 2 to the x, well, it's an exponential function. Only when you say log base 2 of x is a function. But if you say log base 2 of 16, well, it's no longer a function. Now it's a number. It's a 4. So what is the thing that makes it into a function? It is this x that needs to sneak in, right? Allowing for a change of value, consistent change of value, so that you can plot infinitely many points next to each other and produce a line which graphs it. So logarithm is a mathematical operation that it's just like addition, subtraction, multiplication, you name it from the list. And big issue, obviously, is that we are introduced to the log so late, right? You probably, some of you actually had 10 years of math before you seen log. 10 years. Because if you start in the kindergarten with counting and adding on your fingers up to 10 in kindergarten, and then in the first grade, right? You memorize multiplication table in probably second or third grade, depending on the curriculum, right? It is in high school when you see logs for the first time. Some of you, as I said, right, because not all programs from everywhere in the world are the same, some of you spent 10 years taking math courses and then saw the operation that completes the chart, right? So I understand that it's not going to be your favorite, right? It was rushed in in a month, and now you need to be able to do things with it. So we understand the notion of calculating and then being able to undo calculation. Calculating, being able to undo calculation. Calculating, being able to undo calculation. What do I mean by undo? I mean the inverse, right? So log is going to undo exponentiation, and by writing this conversion rule down, it shows clearly in which way the logarithmic function and exponential function are inverses of each other. So now, if I want to think about log base 5 of 625, and I want to calculate this, I will assign this unknown value, let's say, to be x. You can put a, you can put anything. And then you can do your conversion to write that 5 to the x is 625. Now, if you know that 625 is 5 to the 4, by simple comparison, you get that x is equal to 4, which leads you to log 5 of 625 is 4. They're not cute to compute, only when they line up nicely. But in most cases, they don't. Now, as mentioned before, the nature lines itself up with, well, mathematics describes it, obviously. So lines it up so that vast majority of application and things in nature are E base. And then, as I mentioned, some of them are base 10. So your calculator is going to have LOG button and LN button. Now you also know that there is log and ln. So now what is the difference? So this is the segment log versus ln. So here's the only thing you need to know. Log base c of x is ln x. What is ln x? It's a lazy notation for us. It's 2 characters shorter to write. That's all it is. It doesn't have special rules. It doesn't have its own mathematics. ln x is a shorthand notation when the base of a log is e. We have another one for base 10. So this is the connection, which means that any rule, formula, or anything that you learned for log, LOG, also holds for ln, because anytime you see ln, you can rewrite it as a log base c of the same argument that you had before. So what is ln x? ln is just a lazy notation, so we can shorten our writing, because we get to write it so much, actually. So saving 2 characters per line, that's great. The other one is log base 10 of x is just known as log x. If you see no base, it's automatically 10. So this is notation, and your calculators have ln button and log button. They do not have log base 6. They do not have log base 10, base 11 or something. They only have base e and base 10. Now, some really advanced calculators will only have ln. So this is how you know which level of a calculator you have. There is one of those TIs that is scientific, not a graphing one, that will have, that allows you to plug in any log base. So that's the noob level, right? Then your TI 83s, 84s, and so on, they only have LOG and LN, right? And then you have the God tier, right? It's just LN button, and that's it. Now, what do I do if I have to calculate log base 7 of 29, right? I clearly can't use this because 29 and 7, they don't work together, right? 49 would be great. It was just 2 and you're done. So we use what we call change of base formula. Change of base works this way. This is ln 29 divided by ln 7, or log 29 divided by log 7. You can use either one. Change of base, so that you can use your calculator, is log base a of b is ln b divided by ln a, or log b divided by log a. So that's your change of base, so that you can use your calculator to calculate anything. Now, the mistakes happen when you forget to close your parenthesis after number at b. Be careful about that one. You can try calculating this log 729 on your calculator right now. If you close the parenthesis and you don't close the parenthesis, you will see you get a different number. So make sure you close the parenthesis when you type in b value. So in your calculator, this parenthesis over here is the grade killer. Anytime you push ln button on a calculator, it goes ln and opens parenthesis. Then you type in 29 and you close it. Otherwise, you are doomed. All right, so where are we now? We started with the notion that log belongs to the list of mathematical operations and is as good as plus or multiplication, right? We established that the log will undo exponentiation. We came up with, we wrote down the most important formula, which is conversion between exponential and logarithmic. And then we talked about calculation and what is the meaning of ln and log without base, and finally change of base formula. There are two formulas which I call cute formulas, where you learn that log base a of a is equal to 1. So log base a of a equals 1. This means immediately that log of 10 is 1 and that ln e is 1. Now, if you want to prove that this is true, just use the conversion and you will get that a to the 1 is equal to a, and you know that's true. So conversion proves this quickly. The second formula that I call cute formula is that log of any base of 1 is equal to 0. So this means that log of 1 is 0 and that ln of 1 is 0. So please don't leave ln 1 floating around. Is a 0. Make sure you don't have ln 1 in the denominator, because you don't get to divide by 0, right? So there are limitations of what you're allowed to have. And the last thing in this review of logs, and by the way, there's nothing else on logs other than what I listed here. That's your entire pre-calculus chapter 3, right? Well, 3 sections on logs is in here. So 3 formulas that you must know for what's coming in this lecture. Number 1, you can use log, you can use ln. Let's use ln, it's shorter. ln of x times y is ln x plus ln y. Number 2, ln of x over y is ln x minus ln y. And finally, number 3, ln of x to the power p is p times ln x. All right, so you write that on a piece of paper, you cut it out, and you laminate. You make smaller ones for your wallet. You can make one into a necklace, right? Maybe you want to get a tattoo, if you ever consider tattoo. That's a good one. And you will see by the end of the lecture why. Now, in pre-calculus, you used these formulas from right to left. Because in pre-calculus, you wanted to solve equations, and the only way to solve the equation is to use the conversion. Conversion only works when you have a single log. So when you had a whole bunch of logs floating around, you compress them into a single log, you convert into exponential, and then you solve the equation, right? So there was there was a lot of emphasis in pre-calculus on you condensing logs into single. And you probably had, you remember if you took pre-calc, right? Well, it was a year ago, but still. You had a lot of homework assignments, and they all said condense, condense, condense. And then you had the equation 3.5 section, condense, 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 so you can solve it, right? What we need in calculus is expansion. So we need it backwards, right? So we need to be able to expand when you see a product, to write it as a sum of the two logs, when you see division as a difference of two logs, and when you see exponent on the entire argument. By the way, if you are not familiar with the mathematical jargon or whatever you want to call it, sign of an argument, ln of the argument, argument of the square root. So this is what the argument is. Whatever is here, the whole thing. It could be a number, it could be a variable, it could be a function. So it's just the placement within these sine, log, and square root and so on. So anytime when you read mathematical math textbook or paper or whatever, when they say argument of log is just the stuff that is within the log. So when I say exponent of the argument, you can have ln of sine squared. Sine would be the argument, and the square would be exponent of it, which you get to kick outside. Well, we'll see that. So that's what the argument is, and when I say that word, hopefully you will understand. So this is your pre-calculus for logs. And we know that we use logs to undo exponential calculations. And a few of these formulas that you need, the boxed one over here, extremely, extremely important. So now that we are doing this, let's take some derivatives, right? So this is the part 2 of the lecture, where we learned that the derivative of ln x is 1 over x. That's it. It's cool. But this is very basic, right? Because you're limited just to ln x. How about ln sine x? How about ln of, right? So the case that we actually want to know is ln of f of x. And that is your chain rule, right? F prime of x over f of x. Probably this is my favorite formula of Calc 1. And the reason is, people are generally freaked out by logs, right? Because, right, limited knowledge. Look how cool is the derivative. Look at this, guys. You're looking at the screen? Control C, Control V, and then you take the derivative on top. Control C, Control V. That's all it is. So if you want to find the derivative of ln of x squared plus 3x, what do? You immediately write the fraction because it's ln. Control C, Control V into denominator, and then 2x plus 3 in the numerator, and you walk away. This is, it's that simple. Yes?
What if it is more than just f?
Well, then you have the other rules, right? It just spices the things up. But the basic rule, right? Because remember, I can go with the e to the x squared, e to the x squared plus 3. But can I nest 10 functions? Yes. Do we have purpose for it? No. For purposes of mathematical gymnastics, you can do whatever you want, right? So if this is a 5 chain rule, you will keep chaining right on top until you run out of it. So that's not excluded. So here is the red writing. Most of the time we use this one because we have to end with a Boss equation. Boss equation is log any base. Remember that ln is just base e, right? We just talked about it. ln is a single base, base e. But what is the basis 7? What is the basis 3? Right? We have the formula for that. So this is the general case. It's going to be the same. F prime of x divided by f of x times ln b in denominator. I found this formula very useful with people who say, what do you know? I know this formula, right? And then I write it down, and then they're out of arguments right away, while I still have my argument. Ha, ha, ha. Anyway, what is the derivative of log base 7 of secant x? All right. Control C, Control V on the argument, meaning copy secant x in denominator, immediately multiply by ln of the base, which is ln 7. The derivative of secant is secant tangent, which goes in the numerator, and then these secants cancel, and you're done. It's just tangent x over ln 7. There's nothing you can do here. That's done.
I thought you could do the ln of tan x minus ln 7.
There's no ln for tangent.
Oh my god, you can't just add one? Okay.
Nope. Let's go and see another problem. The derivative of log base, let's go with 6 this time, of, you don't like trig, right? So cosine, let's go cosine cubed x. Blue. So, how many of you made this very easy? By doing what?
Moving the 3 to the outside.
Yes, kicking the 3 in front of the log. That's this rule. Right here. Kicking the 3 in front of the log is going to completely take out the chain rule that you have to do if you keep the 3 on a cosine, right? So now the first order of business is to kick that 3 outside, keep log base 6 of cosine x, and now simply copy 3. Derivative is we know that you Control C, Control V, right? You put the cosine down there. We have our ln of 6. And then derivative of cosine is negative sine x. So what is the final thing over here? It's negative 3 tangent x divided by ln 6. Right? Sine over cosine is tangent. and then ln 6 stays in the denominator. Now, if you're a decimal person, you will take 3, divide by ln 6, and come up with a decimal that you plug in there. And it's just negative decimal tangent x. Ta-da! Part 2, done. Right? Part 3. Logarithmic differentiation. We start with an example. Logarithmic differentiation is a procedure. We're not learning a new rule. It's a procedure. So the derivative of cosine to the 8x times the 4th root of x cubed plus 2x minus 1 divided by x cubed times 4 minus x squared to the 5th power. Not a problem, right? Would this be labeled as hard? Obviously not. It's annoying. There's a difference between the two concepts, right? What do we have in this problem? If you carefully look at it, the main rule is quotient rule, very good. And what else do you have within? Two products, very good. There's a product in the numerator and the product in the denominator. And then 3 chains. Great. So it's a quotient, 2 products, and 3 chains. Nothing you can't accomplish by flipping the notebook in the landscape mode and then just, spending about an hour. It's all good. Now I'm going to sound like Morpheus from Matrix. What if I told you that with sufficient practice, you would be able to take the derivative of this mentally and give the answer without any steps, any work, in factored form? What if I told you that this technique of logarithmic differentiation just zeroes out the entire chapter of things you learned, because you would be able to go back to every single section, every single derivative we did so far, look at it, and immediately dictate the derivative, regardless of how complicated that problem is. And just like some martial arts would claim, the more of the opponents and the bigger they are, the easier it is to defend yourself. Sounds good? Shall we just dive into it and see what's the scoop on it? Right? I think that by far, that was one of the coolest things I've seen in calculus. And what I found as I teach this throughout the years, there's not much hype in the book about this. And generally, other instructors don't hype it up as much. Usually I have a few students that become designated derivative takers because they go home, they go crazy to learn this and practice this, and then after that they just go and they freak out people in Calc 2, right? Because most of the professors, instructors, they don't hype it up, right? They say, okay, this is the thing you can do. Here's an example, and they move on, right? And then some of you decide to like really push it far. So we'll come back to this example at the end, and I'm leaving enough space over here to just write the answer without any work, because that's what I promised, right? That's the promise. In order for us to get there, I'm going to work on a shorter example that will have the same features. It's not just going to have, it's not going to be as fluffy as this one. And then we will see what is the mathematics in the background, and then we will see what is that mental pattern that you're observing. Now, keep in mind, what you need to be able to do is to mentally decompose functions using these. That's the only thing. And then taking basic derivatives, obviously, but it's very systematic, so let's go. Let's work logarithmic differentiation on, let's go with x minus 1 cubed times square root of x plus 2 divided by, let's say, cosine to the 4th x. So this is what we would label as a joke, just to learn. We begin by defining y, leave some space, because we need to stick ln there. So we define y function, and we take these roots and things and just make them exponents everywhere. So all I did now is use my square root as a 1/2 exponent, and I use that 4, right, for the entire cosine. And this is when I hit both sides with ln. So I have two sides, and I can hit both sides with ln. This is where the expansion formulas kick in for the right-hand side. Left-hand side is just ln y, so there's nothing there. The right-hand side, every exponent is going to go in front of ln. All of the function pieces that are in the numerator are positive. Every single one in the denominator are negative, because those are our formulas that we had before, right? So this becomes 3 ln of x minus 1 plus 1/2 ln of x plus 2 minus 4 ln of cosine x. This is logarithmic expansion from pre-calculus 1 using those three formulas. I'll go back to the three formulas. Yes?
Just scroll down a little bit, but you're using the product, you're expanding it to the addition. Do you need to put parentheses around the first two terms?
No, because each one individually gets a plus or a minus. And this is what I said. Every single one that is in the numerator will have a positive ln. Every single part of the function that's in denominator will have a negative ln.
Okay.
So in that very first example that was the fluffy one, right? You had a product on top and a product on the bottom. That means two positive ln's and two negative ln's, right? But we'll get that later. So these formulas were used where x was my first parenthesis, y was my second parenthesis, and then the cosine in the bottom was the denominator, right? So that was negative. And then all of the exponents. Now, do you see what just happened? We took product rule, quotient rule, and chain rule, and we destroyed them all. If I take derivative of this line here, do I have any product rules, any quotients, any chain? Nothing. And this is why logarithmic differentiation is the god tier to take derivatives. You don't have to worry about any of those rules. Just ln both sides, and it just takes all of this that had everything, right? We see the chain rule, the chain rule, the chain rule. We see the product, we see the quotient. When you go here, you just have three terms that are added or subtracted. And how hard is to take the derivative of this? Control C, Control V in the denominator, it's derivative on top. Right? Do you see what kind of joke this becomes? It takes literally 2 lines to take the worst possible problem you can think of and make joke out of it. So now, if I take the derivative in this line, because I expanded everything, the derivative on the left hand side is 1 over y dy dx. The derivative on the right hand side is copy 3, that's a constant, and then we have the fraction x minus 1, right? Control C, Control V. Let me just write that the derivative of ln of any function, right, in the argument, is going to be that function and its derivative on top. So my argument was x minus 1, so I put x minus 1, the same, in denominator, its derivative on top is 1. Plus copy 1/2, put x plus 2, in denominator, the derivative of x is 1. Minus 4, copy cosine in denominator, the derivative of cosine is negative sign on top. Now you see that the derivative is not alone on the left side, right? Has 1 over y. Do we see that 1 over y? That 1 over y goes and multiplies the right hand side. But what was y? Y was original problem, right? So anytime you take these derivatives mentally, you get to copy the original problem and then just run the little string in the back and you're done. And it doesn't matter how complicated it is. You just keep track of 2 things. We'll get there. So now, dy dx on its own is y times all of this mess, which is 3 over x minus 1, plus 1 over 2 times x plus 2, plus 4 tangent x. And now you just fill in what y is. Y was the original problem. So dy dx is equal to, original problem is x minus 1 cubed times the square root of x plus 2 divided by cosine to the 4th x times 3 over x minus 1 plus 1 over 2x plus 2 plus 4 tangent x. 3 lines, 4 lines of work. Avoided all of the products, all of the chains, all of the quotients, all it's gone. It's just basic derivatives. So this y, 1 over y, becomes times y, and that's the original problem, because we defined, right? This was your original problem, and we defined y to be that problem. And then we added ln both sides. So that's the y that propagates. Questions, concerns? Yes?
Where did the 1 over y come from?
The derivative of ln y. Derivative of ln x is 1 over x. Derivative of ln y is 1 over y, followed by the chain because implicit differentiation. You're welcome. Yes?
Your final answer would be the original equation next to everything we did.
Yes.
That,
It sounds complicated right now because you have done exactly 0 problems. You copied one and you're still, right?
yeah.
In high school, I used to have this math teacher who was always serious. To me, was funny. A lot of people didn't like and appreciate that. So you as a student would ask a question, oh, I don't understand, and he said, you're not supposed to understand. You go home, you study for a couple of hours, you do a couple hundred problems, and then it will just reveal itself to you. He used to say that all the time. So it's never no questions in class, right? Because you get discouraged after some time with you're not supposed to understand. You have done 0 work up to this point to actually understand this. I'm going to define a way, right, for mental process here. We'll get there. One of the best things is when student was disrupting class talking, right? And he was so annoyed. Oh no, there was student came to the board and did one of those algebraic no-nos when you either cancel something or add square roots or whatever. He drew a line with a chalk on the floor and said, you can't cross this line, right? To go to the board, to make some error like that so everyone else sees the wrong thing, right, and learns it wrong. Now, your grade depends on you actually doing the work on the board more than anything else in class. So that technically means he's going to fail the class because he's not allowed to go to the board ever. The next day, the whole classroom agreed that when the question is posed, no one will raise hand to do it. And he would be the only one. Just to see if he's going to remember, right, that the line was there. Now, the line is still on the ground, right? You draw it with a chalk. So, teacher asks the question. This guy raises the hand. He says, okay, gone. It's like, yes, he forgot. But this is what the student did. He went and stood at the line and then was trying to reach the board. It was still 2-3 feet off. So it created a ruckus. He got him kicked out, obviously, out of class for the day. Yeah, anything. You show up without a square notebook. You see me using square grid. I am not capable to write mathematics on the lined paper because I have 12 years of education in the classroom where if you show up with a lined paper, with a non-square paper, they kick you out right away. Go play ball, school is not for you. Now, coming from a socialist country, right, in socialist regimes, right, where the education is free, only 10% gets to be educated, the rest, no, right? So, right, people are screaming here, yeah, we need to socialize education because then schools will be free and I get to go to school for free. No, you don't. 10% of cognitive elite gets to go to school for free, and 90% of every classroom doesn't get to go to school at all. So there's a difference between socialist regimes and the one that you have now that you can take a loan, even if you're not passing the test at the 10% top. Yeah, you don't know that. So yeah, that's where the things are. Anyway, let's do another one of these derivatives. So I'm going to call for audience participation. So how about you come up with a problem that has a division and all of the stuff in it so we can run this one more time. So what are we going to have in the numerator?
Cosecant.
Cosecant.
Raised to the third power.
All right. Cosecant x raised to the third power. Okay, this is like you're in Subway and just like piling up stuff in a sandwich. So what else do you want?
We have cosecant, and then let's make x the ln of 3x. Is that too nice? That should be that.
Spicy. Okay. So this would be the argument of cosecant. Fine. What else do you want to have? What else are we going to toss in? This is like one out of at least 3 or 4. What else do you want to have in a pile? We don't have to go too crazy, you know, incremental steps. What else do you want to have in a pile? 7e to the 7e to the 8x. Nice. What else do you want to have in this party?
I think you might need to work with the denominator a little bit, guys.
We need a square root. Yeah, we need a square root.
We need a square root. I mean, yeah. How about we make it a 5th root?
Yeah. Yes.
I would say 5th root of what?
Yeah, there you go.
You're allowed to put y in there?
No. In Calc 3? In Calc 3 you get the NZ. All right? So what should we do in the 5th root?
9x to the 7 minus. You have another square root within a square root. Uh-oh.
That's gonna be too.
Not too hard.
It's gonna be annoying.
X cubed.
X cubed
Yeah.
plus 9. All right.
Super spicy.
Okay, so the answer is you just copy this and then you have 3. No, it can be done like this. But let's, take it easy. Do all the steps. So leave some space, y equals, leave some space, and then write your cosecant cubed of ln 3x times 7e to the 8x. Now I'm going to put my 5th power as 1/5 exponent. I mean 5th root as a 1/5 exponent. So I have 9x to the 7 minus x cubed plus 9 raised to the 1/5. Hit both sides with the ln. ln y is equal to, and here comes the expansion. Ready? 3 ln of cosecant of ln 3x plus 7 times 8 of ln of e to the x minus 1/5 of ln of 9x to the 7 minus x cubed plus 9. So this is your expansion. ln e is equal to 1. So that term, that's just 1. And then you have 7 times 8 is 56, but when you take the derivative of that, 56 is just going to die, so that term doesn't matter. Oh, cool. Yeah, e to the x is actually, they cancel, but that's okay. If you are not certain, struggling with algebra on this one, e to the 8x can be written as e to the x, everything to the 8, because the exponents are multiplied. And then you can use this 8 to go in front of ln using the p rule, right, the power rule for logs. And then you have your ln of e to the x, and that's 1. It was in one of those cute formulas I was talking about earlier. Great. It's time for us to differentiate. in respect to x. The derivative of ln y is 1 over y. And then we follow with dy dx chain rule. And now we have a little spicy situation here because we have nested functions, but that's not a problem. Control C, Control V. Right? Control C, Control V. And now the derivative of this in the numerator. Now the derivative of cosecant is what? Negative cosecant cotangent. Cosecant of ln 3x. Cotangent ln 3x. Now you see that the cosecants are going to cancel, right? But you also have to do the chain rule for the inside because you have the nested functions. That's what you wanted. So you have 3 over 3x. That's the derivative of ln 3x. So that's the derivative of the first part. The derivative of 56, 7 times 8, that's 0. So we can say plus 0, minus, and here's my 1/5. 9x to the 7 minus x cubed plus 9 in denominator. Derivative of it on top, 63x to the 6 minus 3x squared. Done. So dy dx alone is equal to y times, now this 3 and 3 will cancel here. We have negative 3 cotangent of ln 3x divided by x. 0 is gone. Minus 5 times in the denominator. Minus x cubed plus 9. And the numerator is 63 x to the 6 minus 3x squared. And all I need to do is to fill in what y is. So dy dx is equal to, y is the original function you gave me. Cosecant cubed of ln 3x times something. 7e to the 8x, thank you. Divided by, it was a cosine, no, it was not cosine, it was a fifth root, thank you, of 9x to the 7 minus x cubed plus 9. And then times what I have here. That's negative 3 cotangent of ln 3x divided by x minus 63x to the 6 minus 3x squared divided by 5 9x to the 7 minus x cubed plus 9. It's already factored.
Well, okay, so my first question is, why is the derivative for ln 3x 3 over 3 and not just 3 over x?
Okay, so here are we have two different situations. There is 3 ln x, whose derivative is 3 times 1 over x, which would work out to be 3 over x. And then we have ln of 3x, whose derivative is, you copy the function as is on the bottom, and then its derivative on top, derivative of 3x is 3, so it cancels down to 1 over x. Now, to prove this further, I know that this breaks down into ln 3 plus ln x by the basic formula that we had. Now, what's the derivative of ln 3? ln 3 is a number, right? You can punch that in a calculator, you get decimals. ln 3 is going to be about 1. So the derivative of that part is going to be 0. Plus, yes, it's a constant. This is a constant, yes. And then the derivative of ln x is just 1 over x. So we do get 1 over x again. Either way we do it. The derivative, so here, see this is your 3x, right? So 3x goes here, and then this is the derivative of that 3x. The derivative of 3x is 3. So 3's would cancel.
Okay. And then there was another part. Does that say minus? Okay, in the denominator it says 9x to the 7.
Minus x cubed plus 9. All right, so I'm going to go to the textbook now and pick one of these problems from homework. And I'm going to just write the answer without doing any of the work, so we can see which way we obtain the derivative without doing any work. So I need you to focus and listen, because there are no steps for you to write. There is literally no reason for you to hold the pen. You need to listen and look and try to connect what I'm saying, which is the way of thinking, to what I'm writing at the same time. As I said, you do not have to learn this, right? That's only if you want to be if you want to know, how to do these things. So I'm just going to quickly find the problem for logarithmic differentiation. They actually don't have many of these around. They don't put too much emphasis on any of this stuff. Okay, so your homework problem 82. Now please focus on what I'm saying and what I'm writing at the same time. And you don't have to write anything. You'll have a chance to copy all of this. Again, no work. So x to the 8 cosine cubed x divided by the square root of x minus 1. That's the problem. Here is the derivative. You can call it f prime, you can call it dy dx, whatever. I know I'm supposed to copy the entire function as is. And then there is this string where the expansion and everything comes in. So the first exponent is 8, which would jump in front of the ln, and then I would just have ln x. So 8, 1 over x. Cosine is on top, that means plus, exponent is 3, that's the coefficient. I'm taking the derivative, the cosine is the function, goes down, its derivative on top is negative sine x. And then finally, square root is in denominator, it's a square root, so half exponent. Its function is x minus 1, its derivative on top is this. Done. And just clean it up. Clean it up. X to the 8 cosine cubed x divided by square root of x minus 1. And then I have 8 over x minus 3 tangent x minus 1 over 2 times x minus 1. Clearly no one will ask you to do this on a test, to mentally find the derivative. No one will ever ask you that. Exam will have a logarithmic derivative, and the procedure to do logarithmic derivative is outlined here clearly. The key is that if you're able to keep in track in your head with the expansion and the basic derivatives, you can take derivative of anything mentally. That's a plus. That's a huge plus to the method. But the method is, you define your function as y, you ln both sides, you expand, you take a derivative of each term. So it's a very structured procedure, right, which is clearly outlined, and you have a video for it. And the rest is, right, you doing the work. But as I said, now we are allowed to go to any section you previously had in this course and just take the derivative by looking at it. At one point in life, you might have struggled with the derivative of x cubed times cosine x. That was a product rule. Copy the first, derivative of the second, right? Well, right now, you just say, oh, the derivative is copy the entire function. So there you go. Times, in here, I have 3, 1 over x, plus, because it's, right, there's no division anywhere, plus cosine goes in denominator, and the negative sign goes on top, and there you go. You will multiply this in the parenthesis, because this is a easy problem. You multiply this inside the parenthesis, and you get what? 3x squared cosine x minus, and when you multiply this, cosines cancel, x cubed sine x. There's your product rule, right? It works on every problem we had in the past. And the way it works with ln's, it kills every product rule, every chain rule, every quotient. But again, it's a procedure where you have to know those formulas, right? Those 3 expansion formulas. And from there, you can just plow through the calculation quickly. And that, oh no, it's not it. I was about to say, and that's it, let's go for a break, but then I remembered. Didn't we start here, right? So now, one more time, I get to write the derivative without actually doing any work. So derivative is, copy the function as is, so cosine to the 8x, 4th root of x cubed plus 2x minus 1, divided by x cubed, 4 minus x squared to the 5th power, and then we have the expansion string. Exponent is 8, so this is 8, cosine x down there, negative sine x upstairs, plus, because it's in the numerator, 1/4 is the exponent, the function is x cubed plus 2x minus 1 down there, its derivative 3x squared plus 2 on top, x cubed is in the denominator, so minus 3 times 1 over x, and this one is also in the denominator, so minus 5, 4 minus x squared downstairs, negative 2x on top. Clean it up. Cosine 8x, 4th root of x cubed plus 2x minus 1, divided by x cubed 4 minus x squared to the 5th power, negative 8 tangent x plus 3x squared plus 2 divided by 4 open parenthesis x cubed plus 2x minus 1 minus 3 over x plus 10x over 4 minus x squared. Done. It's in the factor form. And that's it. Logarithmic differentiation. Bye.